right, so hey everybody, my name is Brian Norman, and I'm here to talk to you about declarative test setup. So this is going to start with a little bit of background. I am a backend engineer at a company called Datasite, where we have acceptance tests or end-to-end API tests that we bundle with every single one of our backend services. Most of these services deal with features for our platform, and those features all depend on kind of like a core set of domain entities. You can think users, projects, subscriptions, things that are like really fundamental to kind of business logic. To execute an acceptance test, we'll often need a lot of these entities to exist already on the platform that we're testing so that the features can work within them. So for example, if you have a feature that's in a project, we need a project and we need some users on that project to be able to execute that test. And when I first joined Datasite, all of this was config driven. So we literally had a config file that was hard-coded in the service with a bunch of IDs of the users, the projects, and all of that data was then manually configured, and it had to be data center specific. So we have a couple deployment tiers, stage, prod, dev, things like that, and we had to go in and we had to manually configure these things for each of those environments. Obviously, this is not a great idea, but let's take a look at what this did look like. We wrote a lot of our tests in Groovy at the time, and so we had this kind of map of maps where we had, each environment listed and then the information about, users in that particular environment, for example. So an admin, for example, we'd have their ID listed as the subject of a jot, and then part of that jot would have the project ID that they were associated with. We had a lot of problems with this. If there were missing data centers, we just couldn't run tests in that environment. For example, we have a data center in the US and one in the EU. None of our tests had any production data in EU. So we would have to go and manually configure all that if we wanted to run tests there. We were also in the process of setting up a new data center in Australia, and so we were going to have to go through all of our services, all through the manual configuration of all of our acceptance tests to get all of that data set up again to be able to run those tests in Australia. In our dev and stage environments, we're pretty rigorous about deleting unused data. And so there's a potential that users could get deleted in dev and stage. Projects could get deleted, and then we'd have to go back in and reconfigure all of that. And then if you wanted to add new acceptance tests, you had to configure more projects, more users potentially, and then you had to do that in all environments. Hope you got them all exactly the same, and then test your test in all of those environments. So obviously this is not a great situation to be in. Some teams were working on kind of a more imperative approach where they had helper functions or classes that would help call the different APIs to create a lot of these users, these projects dynamically. Because this was kind of a team initiative, a lot of this code was distributed across all of the different services. So a service might have its own helper classes and another service might have its own helper classes for all of this. Again, not really a great approach. Because when, say, we needed to upgrade what APIs were called to create users, to create projects, that had to change then across all of the different services. So we wanted to build a DSL, or I should say, I wanted to build a DSL, and I tried to convince everybody we should do this. So why? A DSL is really great because it's declarative. When you look at kind of imperative approach, you're really describing what you need to do to achieve creating a project or creating a user. With a DSL, you can describe what you want and not necessarily how you get it. So it's really about what you want and not how. It's about the results, not the actions. There's a couple languages that are really declarative. HTML is actually one of them. It describes the document, but it doesn't describe how it's rendered. The browser takes care of rendering it. A lot of times you won't even just see styling directly in the HTML document. A lot of that's managed by CSS and tags and things like that. But the rendering, how the document itself comes to be, is all part of the browser. Another really nice thing about a DSL that we could latch onto was that it was abstract. Since we have this DSL layer, we can again kind of separate that what from how. And so now we had a layer for the DSL, and we had that would, as an implementation detail, know which APIs on the back end to call to create users, to create projects. So that meant we could change the DSL and what APIs it was calling without anybody needing to change how they were using the DSL. We could switch to a V2, for example. Another nice thing is, because it is all implementation details, we could add optimizations at various layers of the DSL to kind of improve the performance of the setup. Maybe we would find existing projects because of a unique name, or find existing users because of their unique name, rather than creating them every single time, and we could just leave some of that data behind from test to test. So let's take a sneak peek at what we built, and then we'll get into kind of like how we built it. So this is kind of the basics of what we built at Datasite. Kind of starts with this Datasite DSL block, which takes a client. You can kind of declare users and what their username might be, and you get references to these users. You can kind of create different kinds of projects. Here we have a diligence and a prepare project, which are kind of Datasite specific things. And then you can create roles within those projects for the users, and then you can invite those users to the project. And this is all very declarative about, this is what I want to happen, and there's no API calls here. There's no, I'm calling this version 2 of some API. So a lot of this is enabled by some very specific Kotlin language features that we're going to go over next. And I think the first one that I like to start with when talking about DSLs is actually extension functions. It's usually not what most people go to, but I think that this is a really good foundation for how DSLs work. So an extension function is something that extends the functionality of a class with a new function that's not natively part of that class. This is really nice because you get to use the this keyword in the body of the class, and you can call that function just like it was a member class, and it's resolved statically, like you might see in some helper classes in Java. A lot of times you'll see this called a function with receiver, and that's actually what I'm going to try to refer to it a lot during this talk, and you'll see why. So let's look at an example here. If we wanted to convert swap to an extension function, we would first need to take the list and move it to the left of the name, putting a dot in between the type and the name of the function. And now this has become an extension function of the mutable list int type. The problem is now we no longer have a list to reference, and so we can't use that parameter anymore, and so we have to change to using the this keyword. How this actually gets used is we can just declare a mutable list of integers, and then we can call swap on it, just like it was a function on a mutable list, giving us the result of 321. Kind of taking a left turn, we're going to talk about lambdas. Lambdas are a bit complex to talk about. They're often called function literals. They're functions that are not necessarily defined somewhere in like a class file or in another file, but they're just they're used as an expression themselves. They have their own type annotation within Kotlin that you'll see, and they can just be referenced as a variable, and they can also then reference other variables in the scope around them that they're defined within. So if you define a lambda within a function and there's local variables in that function, you can just reference those local variables. You will often see them passed to other functions, and then this kind of defines what you might hear as higher order behavior. So if you hear like a higher order function, it's a function that takes a lambda. And then lambdas themselves can just be executed as if they were functions, but you need to use the invoke operator function that exists on the lambda type. So let's take a look at an example of a standard library function called map. This is pretty simple from what the function itself does. We're going to define a new mutable list that returns type R when we started with a list of type T. We're just going to iterate through that list of type T, and we're going to have to add something to that new list. But what are those question marks? So the parameter that we need to take here is a lambda. And that parentheses around T, arrow R, is the notation that we have for functional types in Kotlin. The parentheses define your list of parameters that you take, and then the arrow, after the arrow, defines what the return value is. To use this lambda, we can call the invoke function on it, passing it whatever parameters that we want to pass to this lambda. Because it is an operator function, Kotlin just allows us to not even use the invoke function. We can just say parentheses, calling it like it was just some other function that existed. And this completes our map function, where we take some behavior, some lambda, from the caller that describes how we want to transform each element. And then we can iterate over that original list, mutating it, well, not even mutating it, transforming it into a new list of the new types that we want. So if we had an example here of list of hello world, and we just wanted to map that to what the lengths of those strings were, we could use this notation here with the curly braces, string being the type, being the parameter, arrow, what we want to return. Kotlin is nice here again. We can drop the parameters of a function that only takes a lambda. And we can actually just drop the whole parameter itself because it is the only parameter. We can do it.length. And it then refers to the single parameter. So here we have a transformation of a list of strings into their lengths. And there's nothing stopping us from doing multi-line lambdas either. They don't have to be on a single line. All right, now is when we kind of combine these two things and we talk about lambdas with receiver. Having talked about functions with receiver and talking about lambdas, this is pretty simple. It's a lambda with a receiver. It's an extension function, but in lambda form. So let's just kind of take a look at what this is. There's another standard library function called build list that allows you to kind of functionally declare what a list is going to be made of. And so we're going to start with a mutable list of T. We're going to do something to kind of build up that list, and then we're going to return it as kind of just a list type, just kind of that view into a list rather than being a mutable list. Again, what are these parameters though? For the lambda, we have this notation for defining a lambda with receiver, where we can use that same extension function form where the type is now to the left of the parentheses separated by a dot, and then we have some return value. To call this function, we can just say list.builder because it is just an extension function or a lambda with receiver. We can just call it like it was some function already on a mutable list. This allows us to call the build list function and use the this keyword with inside it to refer to that mutable list. And so we can say build list, and we can say this.add, and we're just going to kind of build up that mutable list. And because the this keyword is implicit in Kotlin, we can actually just drop that all together, and now this becomes build list add. And this kind of forms the basics of what a DSL is. This whole lambda with receiver is how DSLs are built. So we're going to talk a little bit about some terminology. Scope is something that I use to refer to the receiver type of Lambda with receiver. It's a lot easier to say than the receiver of the Lambda that you were passed. So we'll just kind of call this scope. And the scope, or that receiver, is really what allows you to kind of control the structure of your DSL. By introducing a new receiver type into your Lambda, you can kind of now say a bunch of functions that are available on that type are now available within your Lambda implicitly. And this allows you to kind of control in a type-safe way what you can do with your DSL. All right, so let's take a look at, again, an example. So if we were modeling Markdown, for example, as a DSL, we might start with a Markdown builder function here, where we take a Lambda with receiver, where the scope, or that receiver, is just this class Markdown. And then we can start creating functions within that Markdown that become now available within that builder. So on the right, you can kind of see we have this Markdown scope that we've opened with the parentheses, and now we can call the paragraph function without needing to reference any kind of Markdown object. We can continue this and add H1, H2, H3, all of the different kind of Markdown formattings. Another nice thing in DSLs is default parameters. Default parameters make it really nice to kind of provide defaults for your DSL, where you can provide a function that might have a bunch of built-in defaults, but allow then the user to kind of override those defaults only if they really want to. So let's kind of take a look at what this would be by looking at what list would be modeled as within a Markdown. So lists in Markdown can be either ordered or unordered. And so we'll need to have, a Boolean here passed as a parameter before we open up another scope of Markdown list. And so this means that we'll just have to always provide a value for ordered. But with default parameters, we can move that value to the function itself to say that this is just by default an unordered list, and if you want it to be ordered, you'll have to say ordered equals true. And then we can add an item function within the Markdown list scope to kind of then allow us to build items into our list. All right, now, unfortunately, there's a problem with our DSL right now. And DSL marker is the solution, but let's talk about the problem. And it's best to just kind of show this, because this is kind of a weird one. If I kind of simplify this example to where I just have paragraph and list, right now, I can add paragraph inside the list. The scope is there. I have the receiver from the Markdown function. I can call paragraph. But what does this actually mean from a structure perspective? Do I get a paragraph and then a list and then a paragraph? Am I trying to add a paragraph to a list? Am I going to get paragraph, paragraph list? It's very unclear based on this structure what my Markdown is going to actually look like. So by creating a new annotation that is itself annotated with DSL marker, we're going to call it Markdown DSL. I can annotate all of the scopes or the receivers of my Lambda. And then Kotlin will only allow me to call a single scope or a single receiver within my DSL, and it's the most recent one. So in this case, paragraph is no longer callable because the receiver that I have within the list scope is Markdown list, not Markdown. And so this provides me some protection at compile time from poorly structured DSLs. All right, so we've talked about DSLs. We talked about some tests. Let's actually build a DSL here similar to what we built at Datasite that kind of models a domain. Since Datasite doesn't really have a public API, I can't really build something off of that, but GitHub has a public API, and it's probably something that we're all very familiar with. So let's take a look at what some of the API entities are. We've got users within GitHub that can be referenced by their username, and obviously there are endpoints that we can call for actually creating users. We've got organizations that kind of act like users, but they are separate and can have users themselves. We've got repositories that kind of live within this owner thing that can either be a user or an organization. And we've got issues that can live then within a repo, which then itself lives with inside an owner. And we've got pull requests that are kind of the same. So we can kind of see from the URL paths what kind of structure that we have for ownership of these different entities. And we can kind of start to build a DSL, just maybe in a Scratch file or something that kind of models what we want this to look like. So we might start with like some GitHub top level function. And then we might say, well, there's probably going to be like a user function in there, maybe an organization function in there that we can call to kind of define a user or an organization. And then inside a user or an organization, we might want a repository function to define a repository. And then, of course, within a repository, we'll want a function to describe an issue or a list or a pull request. Taking this and kind of turning into how we would actually implement it, what we might want to do first is say, all right, what are all of the different receivers of these Lambdas? Because as you can see, a DSL is really nothing more than just a bunch of nested Lambdas with receivers. So we can start by saying, all right, that top level one is going to be our GitHub DSL scope. Next one down is going to be, user DSL scope, and then org and repository. We can kind of take these and then turn them into interfaces. This is usually where I like to start. I also like to use that suffix DSL scope to kind of give them all a similar name so that I know that they're kind of all within the same family of class. And because we know that organizations and users are often treated as the same, we'll create a common interface for them called owner DSL scope. We can then start to take those functions that we had in our sample DSL and start adding them to these interfaces. So we can say we want a user who's going to take a user DSL scope lambda, and we'll then return a user. And we're going to have an organization function that's going to take a lambda with a DSL, an organization DSL scope receiver, and we'll also return an organization. The owner DSL scope is the one that we'll add repository to, because we know that this is something that's going to get shared between the user and the organization. And then down in the repository DSL scope is where we'll add issue and pull request. And this gets us our model. This gets it so that the code is really close to compiling, but it doesn't actually do anything. This just kind of describes the API service for our DSL. And of course, we'll want to make sure that we add in that DSL marker to all of these interfaces so that we can't add a repository inside of a pull request, because what would that be? A really new, cool version of GitHub. So let's look at owner DSL scope. It has a single function here for repository. And now, the other thing about these functions is I've kind of dropped any other parameters. They only take this builder. And that was just kind of for simplification. When you're defining a repository, obviously there's a lot of other parameters, like a name, for example, what you're actually calling this repository that you'll need. So we'll have an implementation of this owner DSL scope. We'll call it real owner DSL scope. It might need some client that it uses to communicate with GitHub. For here in this example, we'll kind of assume that it's a retrofit client. And then we'll want some kind of object that represents the owner that maybe has like, what's the ID of the owner, what's the name of the owner, things like that. Because we assume that an owner already exists within this scope. We can then implement our repository function here. I've added the name parameter here. But you could add a lot of other parameters to the interface as well, and give them like default values for other things, like whether it's a public or a private repository might be something that you might want to add. What's the description of the repository? Those could all be parameters with like maybe an empty string as a default value. And then in the body of this function, we can call client. We can say client.create repository. And there we go. Excellent retrofit error handling. If we wanted to kind of make this a little bit more flexible, we could maybe say, because repositories have a unique name, we'll just look to see if there's already a repository that has that name, and we'll use that one instead. Once we have that repository, there probably exists, or we'll need to implement it, some real repository DSL scope that will then instantiate, passing through the client that we're using for all of this, passing it the repository that we've just created or found, and then called the builder function on it. And this achieves that nesting that we have within the DSL. So once we've now implemented all of our real DSL scopes, we can now know that once the real owner has its repository function called, it's going to call the real repository, and then you'll have the same functionality for issues and pull requests. And that block of find or get is what kind of gives us our idempotent behavior, where if the repository already existed, it would find it. So there's some enhancements that we could make here to this DSL. We might talk about some performance enhancements. Maybe we want to do some prefetching of information. Maybe we want to do some batching of API requests. And so what that might look like is, if we go back to our real owner DSL scope, we maybe say, well, once we get the owner, maybe we'll just go get all of its repositories. Maybe we found that there were only 3 of them. We'll just go make a single request for all of them, and we'll provide that as a map. And then in the body of our function, instead of making an API request, we could just search through that map of repositories by their name. And this kind of takes it down to maybe, a dozen API requests to see if there's already a repository with that name, to a single one that just gets all of that information in a single shot. Another enhancement that we can make, oh, I messed up that slide, and that one, is because we have extension functions, we can actually just add functionality to the DSL without implementing it into the DSL itself. That might be a weird way of saying that we can create functions that are extensions of, say, an owner DSL that help us define what a test repository might look like for your particular use case. Great, you have this nice generic repository function, but maybe for your specific case, you kind of have a form of a repository that you keep creating it over and over again. And so you can create an extension function that might allow you to say, I just want a number of issues and a number of PRs added to that repository, and give it a name, and it's going to go do all of that stuff for you automatically. And then in your DSL, you can just call that function like it was a part of your DSL, even though it's not actually a function on any of the interfaces. You could call this function multiple times to set up a bunch of test repositories. And then because this is just Kotlin, we could just do a for loop. And so by combining Kotlin's language features for kind of this Lambda with receiver to kind of help us structure our code, and then also just kind of combining a little bit of imperative functionality, we can get this nice structured DSL for GitHub and defining repositories. And so what would this maybe look like in a test? Say we had some test suite that we were defining where we wanted to test both a user repository as well as an organization repository. And so we might need those defined kind of in a companion object, so we only create them once during the test. And in this before all, what we might have had before with the imperative version is just kind of this wall of text of a bunch of helper functions that might have said, all right, create a user, create a repo, create an org, create another repo. And it might be a little bit difficult to kind of see, well, this repo that I'm creating in that wall of text somewhere is the owner, right? Organization or user. And it might be a little confusing to say and read, oh, this is a user repo. And so there might be hidden bugs here that you might not see on first glance. And then, of course, heaven forbid you're just using the client directly and calling the API directly, and then, I'm not even formatting this with error handling. This could get real messy. But with our DSL, we've now taken that wall of text and we've given it some structure. We said we want a GitHub, we've given it our client, and then we just have this nice structure of user and the repo that we've created within that, or organization, and the organization and the repository that we've created within that. And this is what Datasite built. Obviously, the example I showed you of the Datasite DSL was a lot more feature-rich. We had a lot more constructs that we created within it. But this is essentially what we have for declarative test setup. This test will run. It'll declare everything that it needs as part of the DSL. And then the DSL behind the scenes will take care of creating everything, finding everything that it needs, and such. And that's it. Thanks, everybody.